I'm Miko Pawlikowski, and this is HockeyStick. Quantum computing. Is it science fiction, hype, or reality? Does it work today? Will it break all your passwords tomorrow? How can you future-proof your career to not get left behind? What does it look like? To answer all these questions, I'm joined by Johan Vos, the author of Quantum Computing in Action, a new book published by Manning, and co-founder of Gluon. Welcome to this episode, and thank you for flying HockeyStick. Johan, how are you today?
I'm fine, thanks for having me.
And the pleasure, I assure you, as you're going to see, is all mine, because I've been waiting for someone to explain this entire quantum computing thing to me for a long time. Let's get right into it. Quantum computing. What is so special about it, and why is it a big deal?
There are a number of things on why I think quantum computing is special and interesting. I think the most intriguing things is that a quantum computer is actually more a computer like how nature is working. So when we think about computers, we think about classical computers that work with zeros and ones, but nature doesn't really work like that. The fundamental subatomic particles in nature, they do not work like the transistors that we use in classical computing. So a quantum computer, while it is often seen as more advanced or so, is actually more basic. And that does not mean that it is easier to create or easier to program, but it totally makes sense from a physics point of view. There are quite a number of similarities and a number of differences with classical computers. And the main difference, and one of the reasons why quantum computers are interesting and are getting attention, is that they might provide huge unseen computing power in a different way than classical computers would do. But there's a possibility to do things on a quantum computer that are technically impossible on a classical computer. And the most common example is then Shor's algorithm. That algorithm allows a quantum computer to factor integers into prime numbers pretty fast, much faster than a classical computer can do. And as a consequence, that might break most of the encryption that's in use today. Now, this is just an example that is often used to catch people's attention, and it is very true, and it may happen one day, but there's much more to quantum computing than this. But if you ask about the hype, I think this explains part of the hype about quantum computing.
Okay, so we've got a little bit of hype for sure. If you put this query in Google, there's a lot of scary sounding things like what you just mentioned, the security going out of the window. But what are some of the examples that might not be covered by the hype that are actually more representative of quantum computing? What do they excel at?
In general, a quantum computer can help you with problems that require lots of parallel computations that are somehow related. Problems that in classical computers would require exponential more time if you make the problem a bit harder, might be solvable in polynomial time, for example, on a quantum computer. I'm trying not to use too much mathematical concepts here, but that is in general the core advantage of a quantum computer. And to Java developers, I often explain this as the parallel streams that we have in Java that allow you to do many computations at once. In a classical computer, we're using different native threads, but in a quantum computer, you can compare it with doing all the calculations at once on the same thread. So the different inputs are processed all together. And that is the core difference between the quantum computer and the classical computer. And then when is this relevant? First of all, in everything that is related to the low-level parts of nature itself, and chemistry and healthcare, where we need to do lots of computations, and especially those that are related to the fundamental laws of physics, those can benefit from quantum computing. So we can use a quantum computer to understand nature better. And there are algorithms being developed to help with some chemical analysis, because chemistry is a bit a weird field. It's pretty hard to simulate even simple molecules and finding out what's happening if you combine even two atoms. It's very hard to do because it requires a huge amount of calculations. So that's something that a quantum computer might be able to do more easily because of their nature with doing many parallel computations at once. They're also good in optimization problems. Traveling salesman, for example, where you have to examine different paths and find the best one. And one example that I think might be available in the more shorter term is quantum key distribution. And people often talk about quantum computing is going to break encryption. But on the other hand, quantum computing is also allowing for much stronger encryption. And that is something that you don't need lots of expensive hardware for it. It's still not easy to do at home. But that is something that I see as a positive evolution that might happen thanks to quantum computing. The encryption that we have today can be enforced by a few orders of magnitude using quantum computers.
So imagine you're talking to a 5-year-old software engineer. They probably have heard of Schrödinger's cat. They probably have heard of a double slit experiment, and that's about the extent of what they know about quantum physics, other than it's weird and strange. Could you try to explain in simple terms things like qubits and what superposition is? Just enough to explain how a quantum computer works at a high level.
That question can be answered by comparing with how classical computers work and then seeing where it is different with a quantum computer. So a 5-year-old software engineer knows that a classical computer works with bits that can be 0 and 1. And in a computer, there are many bits that all are at a given moment either 0 or 1. And the combination of these zeros and ones allows you to do many things. But the thing is, a bit is always either 0 or 1. And the equivalent of a bit in quantum computing is what we call the qubit. So that is the ultimate building block in quantum computers. Now, a qubit can have the value 0. It can have the value 1, like a regular bit. But it also can hold a combination of the values 0 and 1. That is the first and very weird thing about our quantum computers, because what does it mean? It does not mean that it can hold the value 0.35 or so, because when you would measure a qubit, you will either get 0 or you will get 1, very similar to what you will measure on a bit. But during operations, the value can be a combination of 0 and 1. And the main difference is then that where a classical computer works with the value of a bit, a quantum computer is more about probabilities. How likely is it that if I measure this qubit now, that I will measure a 0? And how likely is it that I will measure a 1? While ultimately you will measure a 0 or a 1, you can still do all the computations simultaneously, pretending that the qubit is 0 and that the qubit is 1. And that is a major difference, and that explains the exponential behavior of quantum computers, because with 1 qubit, we can have 2 values, 0 and 1. With 2 qubits, we can have 4 values, 0, 0, 0, 1, 1, 0, 1, 1. And so that's why it scales exponentially. And that is the concept of superposition, which is not something that we invented to make quantum computers work. It's actually the opposite. It is a phenomenon that we see in nature. Some elementary particles, for example, the spin of an electron, have a property that can hold 2 values simultaneously, spin up or spin down. But the moment that you measure it, and that brings us to Schrödinger's cat, the moment that you look, the moment that you open the box, it's in one state only. It will be 0 or 1. So then the fun, the magic is gone. But as long as you keep it in the box, as long as your application is running, your qubit can have 2 values to compute with.
Okay, so I think what we need to explain is basically how do you get from one Schrödinger's cat that is in a box to 2 Schrödinger's cats that are entangled, right? Because with 1 qubit, you can't do an awful lot of good. The whole thing is to get a lot of them, right? And they all need to be somewhat connected. Is that right?
So apart from superposition, which means that 1 qubit can be both 0 and 1 with some probabilities, that if you measure it, it's going to be 0, and other probability that it will be 1. That's one of the strong powers of quantum computing. The other is indeed the concept of quantum entanglement. It's quite different, but the combination is huge. I have, for example, 2 qubits that are entangled, and there are physical operations to entangle qubits. It means that if I send one of the entangled qubits to you or to somewhere on Earth or even to the moon, that is not physically connected to my qubit anymore. And we don't know the value of the qubit. But the moment that I measure the qubit, the value of the qubit in the other place is known as well. You don't know it up front, you don't know it until I measure mine, but then I also know the value of your qubit. And that is not because they had that value initially. No, they had no value initially. So it's not that the value was already there, but we just didn't know it. That's unrelated. And this is, of course, something that one of the most obvious examples is this allows you to create shared keys, for example, because it is the same value that's being sent via a qubit, and you don't know until you open the box. That if I open the box in my place, the box in your place is open as well, and we have the same values. So that is entanglement. So security is one of the things that benefit from this, but just the fact that there are by nature correlations between different qubits allows for a different way of programming. So this is a hot topic in quantum physics in general. It's really tempting to say that information travels faster than light, but it is not. Because if I tell you what my qubit looked like, and if I would tell that to you and you would then compare it, yes, that's indeed the thing, then I would use a Glasgow channel, and that cannot go faster than light. So the information itself is not traveling faster than light. And it's something that I, to be honest, avoid talking about when I talk about quantum computing, because different quantum physicists will chime in and start correcting me and each other. To be honest, to me, it does not make lots of sense. It's just something weird. And I think the key thing to be able to deal with quantum computing is to not try to understand it. I think it was Richard Feynman. If you think you understand quantum physics, then you don't understand it. And it is so weird that it helps giving up trying to understand it. The good thing is that if you just look at the mathematics, then it all makes sense. And if you don't want to do the mathematics, that's totally fine. Then you should just accept that those who did the mathematics did their homework correctly. So superposition and entanglement are real things, but it's extremely hard to intuitively understand what it actually means. And the math behind it is also not simple. So that makes, I think, quantum computing something exotic, especially to developers.
Yeah, I think for me, it was the double slit experiment. When you go and do it and you can see the results that makes no sense, you're starting to think that, okay, something's not quite as logical and intuitive as we all thought. But
Exactly.
that's an experience for a lot of people, right?
True, yes. And you clearly see what is happening, that there are interference patterns. There's no doubt that they are there, but you don't understand it because how our day-to-day observations of how things work do not easily explain this. How can a particle be a wave and a particle at the same time?
What kind of hardware, we're going to talk a little bit more about the application side of all of this, but I'm just curious, in terms of actual quantum hardware that you can lay your hands off, let's say that you're lucky and you're at one of these companies working on it or some university, how many qubits does it have at the moment and how expensive is it to run?
So it's definitely very expensive. The number of qubits, it used to be the discriminator to say how good a quantum computer is. And then, for example, IBM had for a long time this limited number of quantum computers that they made available via their cloud infrastructure. Those had 5 qubits. And gradually, the quantum computers are getting more qubits. We're talking now between 100 and 1000 qubits, but that number itself is not entirely irrelevant because there's an important concept in quantum computing, which is error correction. It's so fragile to operate a quantum computer that the error rate is pretty high. So instead of just talking about how many qubits, it's better to get some noise and produce wrong results. So the quality of the quantum computer is more than just the number of qubits. And that is a discipline in quantum computing hardware that's under heavy research, and there on a very frequent basis, there are new papers about a breakthrough in the new algorithms or new hardware, especially for creating qubits with more error correction. I wish it was simple that we could just plot like the clock speed of a CPU, but there's no consistent definition yet. IBM had this quantum volume defined, but not everyone is using it. But it is the indication of how powerful quantum computers are is not something trivial. But it's clear that they are getting better and better. That's for sure. The question is, how fast are they getting better?
Okay. So for someone who maybe picks up your book, they're going to spend most of their time in a simulator at the moment. Is that right?
So one of the good things about quantum computing is that it is easy to separate the software and the hardware. We do understand how the hardware works because that's just the fundamental laws of nature and quantum physics. And we do know, especially from experiments with small quantum computers, that it is indeed working like this. And now that we know that, we can create software on top of classical computers that simulate a quantum computer because we know the rules. Of course, this is going to be much, much slower and especially requiring much more memory than a real quantum computer. But the basic rules are known and we can program them in a quantum computer simulator. And typically today, if you write software, you do that in a higher level programming language where you then leverage the lower level concepts. And that is what you do in a quantum simulator as well. You write code. In most of the cases, almost all cases during development, that code is being executed on a quantum simulator, but the same code can theoretically also work on a real quantum computer. So the moment that quantum computers are much more available, the code that you write today and that you run on a quantum simulator will also run on a quantum computer. If that was not the case, then I would not recommend software developers to start with quantum computing today. But because we can already do it today, we can create quantum applications. It gives a huge advantage to those developers who are already dealing with it, because the moment that quantum computers are more powerful, more available, those developers can run their applications almost immediately on the quantum computers, whereas others still have to start learning and writing code.
So before we jump into how different it actually is to write that kind of code to classical, we should call it programming language style, tell us a bit about your book. As I started reading this, it came across to me as a very applied kind of book. You talk about how there is a lot of resources that have to do with the very complicated, strange physics of that. And there's also a lot of hype, and your book is trying to be an applied guide that's neither of these things, gives you enough background, but also doesn't buy into the hype. Is that the right impression of the book?
That was exactly the goal. So I'm glad that you have that observation, because that was the goal of the book. I think it's practical as it can be, because I don't think most of the people who read the book have a quantum computer on their desk. So it's not that it's as practical as Python for Dummies, for example, where you can use it in practice. But it's mainly targeting existing developers who want to know how their day job will be impacted by quantum computing. How can they leverage it? How can they benefit from it? What are the expectations? What's clear that quantum computers are not a solution for everything. And I think by explaining how the quantum computers are working, which is non-trivial, the reader gets a better idea. And I try to minimize the maths in the book because it doesn't matter. It might help in understanding, and therefore I wrote this quantum simulator, and the code is open source. If you really want to know how it works, you can look at that code and then you understand the underlying things, but it is not needed. And that is something that in the software world that we often see, that people are using libraries. For example, in the Java world, there's a huge ecosystem with lots of libraries, and people can use those libraries. And I think it's then important that they know what are these libraries doing, what problems are they solving, how can I benefit from it, and what do I need to do to use them. But you don't need to know how exactly they are solving the problem, because then you could, write everything yourself indeed. So I think in that sense, it's targeting the pragmatic developer. I want to know when I can use this, how I can use this. And it's good to understand a bit of the background on why this is working, but you don't need the PhD in physics or mathematics or so. That was the main target of that book. And I think it's actually funny why I did this. I did my PhD in physics, but then I moved over to the IT industry, because for my PhD, I needed to write software. And then there was a new software language, which was Java, but it didn't work on Linux. And I had a Linux workstation. So I, together with a bunch of people, reported Java to Linux. And then I rolled into the IT world, and yeah, I'm still there. But when Jim Weaver, who is now developer at quantum computing at IBM and a fellow Java champion, a good friend of mine, asked me to do some joint presentations about quantum computing, then I said, oh yeah, that's fine. I didn't know much about quantum computing, and I think the best way to really learn or get a deep understanding of quantum computers is to write one in software. I do not recommend that to everyone, but writing a quantum simulator is really helpful if you want to understand how it's actually working. It gives a better understanding, and I think it also helps in explaining it to people.
That makes perfect sense. Would this be an accurate representation then that this is for a pragmatic developer who also wants to future-proof their skills by learning this, so that, like you mentioned, when they become ubiquitous at some point, and hopefully they're still alive by then, they can use that. Are there any applications that quantum computing programming can give you today in terms of production use? Is there anything that you can actually apply it to in your real programmer life day to day?
The real practical examples require more qubits. So in the scientific industry, you can already do some work to get a better understanding about, for example, how nature works. And that is possible. But the applications that are envisioned typically require much more powerful quantum computers than we have today. There is an exception though, and that's what I mentioned earlier, the quantum networking. That does not require many qubits. As long as you can send one qubit from one place to another place, you can communicate in a secure way. That is something that's already being used today in commercial applications, and there are specialized companies that create devices that generate entangled qubits, for example, send each one of them to a party, so they can generate a shared key. And as a consequence, they can communicate in a secure way. So that is something that's used in a number of places, mainly for demonstrations. There's a great team at the University of Delft where they are doing a proof of concept with the port of Rotterdam, I believe, and with telco operators as well, because ultimately the qubits need to be sent over the telecommunication network. So that is something that's at a small scale, but it can be used today.
Can you tell me a bit more about how that actually works? Because what I'm picturing is someone with a fridge having two entangled qubits, packing one up, using FedEx to ship it to somewhere, and then you have this change of that you can detect on either end. How does it actually work in practice? You mentioned about sending the qubits. How do you send qubits?
The good thing is that the qubit itself is not a physical concept. It's just a logical concept that has a physical representation. And everything in nature that can have two states simultaneously, as I said in the beginning, if you measure it, you will always measure one state, but it carries two states with each having its own probability. that is a good candidate for being a physical qubit. So different quantum computers use different kinds of qubits for their hardware. It's often superconducting qubits are used, but trapped ions are also used because they have this physical property of allowing a superposition state. And for communicating qubits, you can use photons, which can be transmitted through fiber. And that is a great advantage because that means that we can use a large part of the existing telco infrastructure. So if you put a photon on your part of the fiber, you can send it to your friend at the other side of the fiber. It can't travel long distances yet, but you can have repeaters in between them. It's an interesting technical challenge, but it's something that, at least in labo experiments and on smaller scales, number of kilometers is proven to be working.
Okay, that makes a lot more sense than my picture of a freezer with entangled atoms sitting in there. And probably better than sending them by pigeon. Okay, so let's jump into what it actually looks like in practice. The part 1 of your book was the intro to the quantum computing. Then you introduce in part 2 quantum computing concepts, a lot of what we talked about. And then part 3 is the getting your hands dirty, code examples, algorithms, and all of that. So let's start where we always start. What does a hello world look like in the quantum computing world?
Again, there are some similarities and some differences with classical computers. Especially in my book, I try to focus on the similarities because that makes it easier to understand and to use by existing developers. And I think at a low level, the similarity is that a classical computer, if you write a hello world, the code, whether you write it in Java or Python or Rust or whatever, that code is being translated into machine code and is ultimately a number of zeros and ones that are converted because some gates are applied. So a typical gate in a classical computer is the NOT gate or the AND gate. And so every hello world application is translated into binary operations on bits, and the binary operations are executed by gates, by logical gates. And the concept in a quantum computer is the same. The difference is that whereas in a classical computer, the input of the gate, for example, we have a NOT gate, and if you have input 0, the output of the NOT gate will be that the bit is now 1. And if the input was 1 and you apply the NOT gate, the input is 0. And with this limited number of gates, it's proven many times that with a limited number of gates, you can create a whole logical computer. Same applies to the quantum computers. With a limited number of gates, we can create quantum applications. But here, if we compare the NOT gate and we move that to the quantum world, if our qubit holds the value 0 and we apply the NOT gate, then the qubit will hold the value 1. Now, when I say hold the value, that actually is short for when the qubit has a state that if we would be measuring it, in all cases, it would guaranteed result in a 1 being measured. That is what I mean with the qubit holds 1. So when the qubit holds 1 and we apply the quantum NOT gate, if we would then measure the qubit, we would measure 0. And vice versa, if it's 0 initially, and then we apply the gate, it will become 1. But here's the difference with classical computers, because a qubit may hold a combination of 0 and 1. If we apply the NOT gate, we will again have a combination of 0 and 1, but with different probabilities than before. The approach is the same. We apply gates to a number of qubits, and that is at a very low level. And at a higher level, we instruct which gates do we want to use on what bits at what moment, similar to how a classical hello world is going to tell the CPU, load this value in register 1, load that value in register 2. do an AND, and the result is in register 3. And everything on top of that is high-level programming. And that's the same for quantum computers. Everything on top of the qubit arithmetic is higher-level programming, which you can do in your language of choice, actually.
So just a thing that I don't think I understand is that classical computer, you've got the gates and you go one cycle, you store something in a register. In a quantum computer, does it work the same way? You do one cycle, it goes through all the gates, and you have some kind of equivalent of a register that does the observation at the end of it? Or is it different?
The registers are qubits as well. So you do operations just on the memory like you do in the classical computing. In a classical computer, whether it's in main memory or a register, it is a bit. The thing with the measurement is that you only do this at the end of your application, and you do that only once. You can't peek inside a quantum computer. With a classical computer, and that's a big difference, you can inspect the values at every moment, and we have great debuggers. I'm a big fan of GDB to check on every step what are my registers and so. You cannot do that on a quantum computer. The moment that you look, it's gone. At least all the superpositions are gone. You will only see zeros and ones. And that's again the analogy with Schrodinger's cat. The moment that you open the box, the cat is either dead or alive. The observation, the measurement, is something that you can only do at the very end. And at that moment, all the qubits will be measured as either 0 or 1. And the key thing in creating quantum algorithms is to manipulate those algorithms that the end result will give you information about what you were actually looking for. And that is done by applying mathematical algorithms that will amplify or cancel things. You want to understand something. If the outcome that you measure is 1, it means that what you were examining has this characteristic, and if the outcome will be measured as 0, you want it to be matching with the other characteristic. And initially, there might be, for example, 50% chance that you would measure 0 and 50% chance that you would measure 1. If you then measure it, you don't know anything because it looks just random. But by applying the correct gates, the result makes sense. And I do understand that this is quite different from classical computers. The 0 and the 1 that you measure in a classic computer corresponds to what you really want to measure. Whereas in quantum computers, it often gives meta information. And that is why, apart from the hello world, this is the first thing that I often describe, and it's in the book. No real practical benefit, but which explains why it is sometimes useful to manipulate the input and the output, and then you measure something, and then you know something about the problem that you were trying to investigate.
For anybody for whom words Deutsch and Jota don't necessarily mean anything, could you give us a little bit more of what the algo actually is like?
Yes, absolutely. I try to simplify the parts that are not relevant to developers, but I try to avoid making fundamental quantum physics mistakes. So I'm simplifying things here. So that was just my disclaimer in case. So the Deutsch algorithm is, or the problem that's trying to solve there is fictive problems. We know that we are given a function. We don't know if it's a constant or a balanced function. There are 2 constant functions and 2 balanced functions. And we can only make one measurement. So suppose that we measure the result of applying the function to the value 0. If we then get as a result 0, then we still do not know is this a constant function or a balanced function. Because if we would apply, but we're not allowed because we had only one chance, but if we would apply the function to the value 1, and if we would measure 0 again, then we know, yes, the function is always returning 0, it's a constant function. But if we would apply it to 1 and the result would be 1, then we know that it's a balanced function because applied to 0, it gives 0, applied to 1, it gives 1. So that's a silly problem, But it shows that if we want to know this in a classical way, we need to do two function evaluations. And on a quantum computer, if we can use qubits, where those qubits can have a superposition, we can prove and also show, so that's where we show the code how it is shown, that only one function evaluation determine if it's a constant function or a balanced function. And that is because we apply it to a superposition of 0 and 1 and then do some operations so that we are guaranteed that after the operations the value is 0. Then we know, for example, that it's a constant function or a balanced function. So we actually need pen and paper to follow this, or I think it's explained well in the book and you can run the code. But the key point here is that we've proven that there is a kind of a problem, a completely useless problem. There is at least one problem where we need two function evaluations on a classical computer to solve it, and we can solve it with only one evaluation on a quantum computer to solve it. Now we can extend this to the Deutsch-Jossa, and then you can easily prove that you will exponentially need to do more function evaluations on the classical computer and only linearly more evaluations on the quantum computer. So that is a simple example that shows that there are problems that require less steps on a quantum computer than on a classic computer. And that is, I think, one of the root advantages of quantum computers. And it also immediately shows that this is not applicable to everything. It's not applicable to the user interfaces or so. It's to a special kind of problems that scale exponentially on a classical computer. And you can prove that they scale sub-exponentially or linearly on quantum computers.
Yeah, I think this is becoming very clear from what you're saying, that the quantum computers are not just, as some people like to paint them, a replacement or an exponential improvement on classic computers. They're going to work on very specialized problems where they make sense, and they're going to be narrowed to that corner probably for a very long time. I think you mentioned also Shor's, and I think I remember Grover search. This sounds a little bit more applicable, don't they?
Yeah, real applications with real benefits. But then the drawback is they're much harder to explain. Adding to what you said, and that's indeed right. So quantum computer is not something that's going to replace your desktop computer or laptop or mobile phone or so, but I actually compare it more with in today's computers, and for a long time already, you have a CPU that's doing lots of work, and it's getting more attention recently. I've been using this example for a long time, but there's also one or more GPUs in most computers. And for some tasks, CPUs are extremely well suited, and for other tasks, GPUs are much better. And I think the same applies to quantum computers. And I envision that in the potential applications or computers of the future, you will have a combination of CPUs, GPUs, and then QPUs, so the quantum processing unit, where the different processing units are executing tasks that they are very well suited for. So for the vector operations, you would go to the GPU. For the typical operations, you would use the CPU. And then for operations that require lots of exponential scale up, you go to the QPU. And then the cool thing is that as a developer, you can leverage the benefits from the CPU, the GPU, and the quantum computer without knowing all details about them. I think most people who write, for example, AI applications, they don't know the individual instructions that the GPUs have. Same with quantum software, you do not need to know all the low-level gates and details about quantum computers, but applications should know that they can benefit from different processing types. So that is where I think that there's a place for quantum computers, for classical computers, for GPUs, and so in typical applications.
I think we're gonna have potentially also like the TPUs, I think they call them, like the ones that are like GPUs but work on lower resolution so that they're better suited for like LLMs, and the
Yep.
QPUs as well. So back to my question about Grover search, for example. Let's maybe just see what's the potential of an algo like this, and how does it work like very high level?
Yeah. It is more tangible, it's more down to earth than the Deutsche algorithm. But it's also, I have to be honest that the name itself is a bit misleading. And especially if a marketing department was to sell Grover Search, then it would probably say that this is going to speed up all your searches by a multitude. But the search itself is, as I said, a bit misleading. The algorithm allows you to find an element in an unstructured list obeys to a specific rule. So if you have a list of 1000 elements, entities, whatever, and you apply a function to those elements, and if there's exactly one element of the whole list where that function would say true, and in all other cases it would say false. So doing that is faster with Grover search than any classical algorithm can realize. For example, if we have, let's say, a very stupid example would be, we have a list of 100 athletes, and one of them is the world champion in the 5,000 meter. So the function that we apply is this person the world champion in the 5,000 meters? So for all of them except for one, that value will return 0, and for one, the value will return 1. If we would do this on a classical computer, there are extremely optimized search algorithms, but still it would be, in best case, linear. So the moment that we get more, if the list becomes bigger, then on average, we will have to do more searches, linear with the input. And on a quantum computer with Shor's algorithm, we can prove that we need to do more evaluations, but instead of linear, it goes with the square root of the number of evaluations that we do. So it's definitely showing a speed up compared to classic search algorithm. And I think going with the square root instead of the whole number is a major improvement. But as I said, it does not replace your SQL search query. It's really for simple searches where you know that there's only one element in the list that will result in that you're looking for. So it's not that give me a list of all people older than 40 years old who live in this city or so. It's really more the example of give me the one element in this list that is the world champion in the 5,000 meter or so. That is a Grover search, which is definitely useful. So it's more down to earth and it's proven to give an advantage over the best known classical algorithms.
So let's jump back to the QPUs. I was going to ask you for predictions for the future, where you see all of this going in terms of hardware and applications, and maybe in 1 and 5 and 10 years. You hinted already at that, seeing the QPUs integrated in everybody's desktop. What else do you predict is likely to happen? What's your best guess? What do you expect to happen, let's say in 5 to 10 years from now?
I think the quick win, and then we're not talking 5 years, it's sooner, because it is actually already there, but on a limited scale, is the quantum networking with possibility to do quantum key distribution and to do secure communication, creating a shared key between two parties. That is something that I think will become more widespread in the next few years. Because the limitation there is the hardware is available. You only need 1 qubit to make this happen. The limitation is more the network and the quantum repeaters and so, but that is less of a technical problem than creating general quantum computers. So that's where what I think is going to work in the short term. The bit longer term is, I think, more specialized algorithms that are targeting a specific task, and that can be, for example, optimization algorithm, traveling salesman, which is extremely interesting for some companies, or specialized financial algorithms for stock market things, or specialized physics or chemistry algorithms that are then applied on a dedicated quantum computer that's really optimized to solve this particular. That is then more or less a combination of hardware and software. So the hardware is more or less pre-programmed to run that specific application. I think that is what we will see in the medium term. and yeah, let's say 5 years or so. And then the more general quantum computers, which are completely independent from what software is going to run on top of it. It's not that I have a personal opinion about it, it's just what I read from people who are dealing with the hardware that they find realistic. And then depending on what your source is, you will see some hardware engineers will say that it's going to be available in 2 years. Others are saying that it's never going to be available. So my rough guess is 5 to 10 years. Then there's a fair chance that Shor's algorithm can be applied at a large scale, which is of course very worrying if by then you're still using algorithms that are vulnerable by Shor's algorithm, or actually worse, if the data that you're using now for communication is stored somehow, that data can be decrypted by quantum computers when they're powerful enough. So the time frame about when Shor's algorithm, for example, is going to be available is maybe a bit misleading, because even if it's only in 10 years from now, that does not mean that your data today is safe, because it's not that hard to snoop data from a network and store it locally. And then once the quantum computers are powerful enough, they can decrypt that data, and that can give quite some interesting information about secret conversations in the past. When I say that it's going to take at least 5 years before Shor's algorithm is applicable, do not want to say that people can use classical encryption like AES and so for the next 5 years without being worried. I think we should be worried today already.
You should be worried. And also with all the leaks where companies lose their entire databases and they say, oh, don't worry, it was all encrypted. That's the same problem, right?
Yes, absolutely. That is very dangerous. More companies and organizations are realizing this. For example, Signal, the messaging application, is already using both quantum cryptography algorithm next to the existing algorithm to encrypt the data, because if data going from and to Signal users is put somewhere on the hard disk, that's safe. That cannot be decrypted with a quantum computer anymore. You never know if there's going to be new algorithms being found out, but a number of companies are now following that example and already enhancing their encryption algorithms, which I think is a very smart thing to do. I still think that in the end, it will still be better if they would use quantum key distribution and quantum encryption, because then a quantum computer can not break quantum encryption. So then they are still safer. That's can only be really rolled out practically when quantum networking is rolled out across the globe.
That's an optimistic note to wrap up the episode on. Hopefully you're not too scared. For anybody who wants to go and check out the book, once again, it's called Quantum Computing in Action. It's published by Manning, so you can get it from manning.com, or you can go to your usual book provider, and it's absolutely worth a read. My guest was Johan Vos. It's been an absolute pleasure, and I hope to see you again.
Thanks. It was really fun to talk about this.